Hello everyone, my name is Jason Gregerson. Welcome to the next video in your Calculus 2 video series. Today we're going to continue on talking about representing functions as power series, and in this video we're going to focus on the second goal, using differentiation and integration to find the power series representations for some new functions. Alright, so let's go ahead and get started. Alright, so the big idea is that we can differentiate and integrate power series term by term. So we have a fancy formula representation for this idea. So here are our formulas. And what we can see in this first example is that if I have the derivative of this series, that I can pass that derivative operation inside the summation to take the derivative of the argument of the summation. And same thing with integration. Now, we've seen this kind of property before with differentiation and integration. You've seen that the derivative of the sum is the sum of the derivatives, and maybe applied it in some small cases. This, however, extends that to an infinite series here. So, how do we actually use this property? Well, let's look at a series that we know. Here we have a power series representation for the function 1 over 1 minus x. And it's represented by this series. Now note, you might have seen this series before, starting with n equals 1, and then looking at the sum from x to the n minus 1. But you should understand that if we're only changing the iterators like that, then we're actually just getting a different representation for the exact same series. So oftentimes when we work with power series, we like our summation to start at n equals 0. They don't have to, but sometimes we like to use that notation. So here is our known series. And the idea is we have this equation. We have 1 over 1 minus x is equal to this series. Now because I have this equation, I can certainly operate on both sides of the equation. So what I'm going to do is take the derivative of both sides of this equation. Now to do that, I'm going to represent that left-hand side as 1 minus x raised to the negative 1 power. And if I take the derivative of both sides, well, the derivative of the left side is going to be, well, I have that function raised to the negative 2 power, multiplied by my negative 1 in the front, but also times the derivative of the inside function. And the derivative of 1 minus x is negative 1. So in that case, my negatives would cancel. So I will get 1 minus x raised to the negative 2 power, or 1 over 1 minus x squared. Now, that should be equal to the derivative of the right-hand side of my original equation, which was the derivative with respect to x of my series. But what my property is telling me is that I can pass that derivative inside my series notation and really just apply the derivative to x to the n. And I could use the power rule to take the derivative of the argument of that sum. So this would be n times x to the n minus 1. And so that's the summation notation version of this series. I could certainly do it that way, but I could also actually look at the expanded form and just simply take the derivative of each of the pieces term by term. So I could say the derivative of 1 is 0, plus the derivative of x, which is 1, plus the derivative of x squared, which is 2x, the derivative of x cubed, 3x squared, plus dot, dot, dot. And that would be the expanded form representation of this series. Now, one thing to remember here is that my original equation was only true when the absolute value of x was less than 1. And that continues with this new series. So now what I can see is I have this new function, 1 over 1 minus x squared. And notice that I can't get to this function like I had in previous videos by multiplying my original function by something or making a substitution. This is actually a pretty different function here. But now I know the power series representation for this because I can use this derivative property. Now I know the series for this function is the sum from n equals 0 to infinity n x to the n minus 1. Or in expanded form, 1 plus 2x plus 3x squared plus dot, 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 when the absolute value of x is less than 1. Now the other thing I want to point out here is if we look at this series is not geometric. So now I've been able to find a way to represent a function with a series that's not geometric. So I've actually expanded the series I can work with here as well. I now know that this series, even though that it's not geometric, I know this series converges to this function when the absolute value is less than 1. So that's an example, an application of that differentiation property. Let's see if we can do the same thing with integration. We'll work with that same original series, but now if I integrate both sides, what do I get? Well, when I integrate 1 over 1 minus x, I will get negative the natural log of 1 minus x. But that should be equal to, well, the integral of my series. But now I can pass that integral sign inside of my summation notation. And so I can use my property to say this is really the series that looks like, well, I'm integrating x to the n, which should be x to the n plus 1 divided by n plus 1. And that's the way I can generate that sigma notation version of this series. But actually, I could also write an expanded form just by integrating it term by term. The integral of 1 is x. The integral of x is x squared over 2, x cubed over 3, so on and so forth. But I do have to be a little bit careful here. Right? When I integrate something, I have a constant of integration. So really, I should also include a plus c here. So maybe a plus c plus dot, 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 dot here, where I have this constant of integration. Now, I really don't want to keep that constant of integration there. So what I can do is say, okay, negative the natural log of 1 minus x is equal to this series. And so if I choose a value of x, I should be able to find the value of c that makes this relationship true. Now, if I have to choose a value of x, and once again, I'm restricted to the absolute value of x is less than 1, I'm going to choose x equals 0 because it makes my computation extremely easy. If x equals 0, and remember I'm just choosing that, I can plug that into both sides of my equation and I should get a true statement. So on the left-hand side, negative the natural log of 1 minus 0, negative the natural log of 1, which is equal to 0. So I would get 0 is equal to, and then when I plug in that x equals 0 on the right-hand side, that entire infinite series becomes basically a series of zeros. 0 plus 0 squared over 2, 0 cubed over 3. That all goes away, and all I'm left with is equal to c. And so now I've found the value of c that makes that equation true. So in this case, the c actually goes away. But in general, when you integrate to find a new series, you do have to find out that specific value of c. So the last thing I'll do is I'll just multiply through both sides by negative so I can clear this negative sign. But when I do that, I will get the natural log of 1 minus x is equal to x is equal to the series that I can define once again using sigma notation, which is x to the n plus 1 over n plus 1, or I can define it using expanded form, x plus x squared over 2, x cubed over 3, x to the 4th over 4, plus dot, 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 dot. And once again, now I have a series representation for a more complicated function, the natural log of 1 minus x. And I was able to use that using this property of integration. All right, one more. Let's see one more example. Find the power series representation for arctangent. So now I've got to work backwards. Now I'm just given the function, and I have to somehow manipulate this till I can find a series that I know and then use my properties. So here's what I'm going to do. I'm going to look at my function is equal to arctangent. Now I have to recall what I know about this function. One thing I know is that the derivative of arctangent is 1 over 1 plus x squared. Now when I see that, I look at 1 over 1 plus x squared, I realize that that's like one of my geometric series, and so I should be able to generate the series for 1 over 1 plus x squared using a substitution of my known series. So I will start with my known series. This one is equal to 1 plus x squared plus x cubed plus dot, 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 dot. That means if I use substitution and I replace x with negative x squared, then I'll get 1 over 1 minus negative x squared, or 1 over 1 plus x squared, which should be 1 plus negative x squared plus negative x squared squared, negative x squared cubed, plus dot, 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 dot. And I can simplify this if I look at all the individual terms. If I'm raising them to odd powers, then that negative sign will stay. If I raise it to even powers, I'll turn to a positive. So I have an alternating series here, and it's going to look like 1 minus x squared plus, And I also recall that when I raise powers to powers, I multiply those exponents. So I get plus x to the 4th, minus x to the 6th, plus so on and so forth. So now I've generated the series for 1 over 1 plus x squared. But now how do I get to arctangent? Well, arctangent would be the integral of 1 over 1 plus x squared. So now I can say that arctangent of x is equal to, and I can integrate this series term by term. So integral of 1 is x. Integral of x squared is x cubed over 3. X to the 5th over 5. X to the 7th over 7th, so on and so forth. And now I have the series representation for arctangent. Don't forget, we have our plus c in there somewhere, and so we do have to find that value for our constant. To do that, we're going to choose a value for x and see if we can find the value. So once again, we'll choose 0. Arctangent of 0 is equal to, plugging in 0 to the right-hand side gives me a whole bunch of zeros and an extra value of c. And then we need to recall that the arctangent of 0 is equal to 0, so that tells us our constant is actually going to go away. When everything is said and done, we're going to be left with arctangent of x is equal to the series x minus x cubed over 3, x to the 5th over 5, minus x to the 7th over 7th, plus dot, 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 dot. So here we have the series representation for arctangent. All right, that concludes this video. Thanks for your time.